In this video, we're going to discuss this spreadsheet that I've developed over the years, and it calculates many of the 2x2 table statistics that you will need. First, before we do this, let's look at our sample. We're going to take data from parents who've said how much time their children have spent during the week on various activities. For example, here's a distribution of study hours, reading, TV, computer, and sports. So really we're going to call that outdoor. So we're going to actually make a cutoff here about 35% of the time. And look at this subset right here. We're going to give a 1, call it outdoors, 1, and this is 0. So we're going to recode sports hour lowest through 35 is 0, else it's 1. And we're going to code it into the variable outdoors. Then we're going to do a crosstabs of outdoors, and we have the myopic status of the children. So we get this table right here. Now, to use this table in this spreadsheet, you have to be pretty careful about the way that you enter the data. Order is important in this case. The green is spaces for numbers that you have to fill in. And so in this case, disease is going to be, we're going to call that myopia. And exposure, we're going to call that outdoors. And there's a plus and a minus, so this would be outdoors, not outdoors, myopia, not myopia. Now, notice that the table in SPSS doesn't go that way. If a person, so you kind of have to do it cell by cell so you don't get yourself confused. So let's look at a person with that is outdoors, spends time outdoors, and has myopia. What's that number? Outdoors 1, has myopia 1, that's 82. So we're going to put an 82 into this cell. So we have outdoors, but not myopia is 736. Outdoors, but not myopia is 736. And then we have not outdoors, not myopia, 2212. Not outdoors, not myopia, 2212. And finally, we have not outdoors, but myopia. Not outdoors, myopic, 518. Now notice that the totals were updated. We have 3,548 total subjects, 3,548. So our data match. You should always be sure your data matches the totals, and so you get the right answer. Now, these little numbers over here are marginal totals. So there's 818 that had outdoor activity. There's 2,730 that were less than that percentage outdoors. Spent less than 35% of the time outdoors. Then we have the total number of myopics, the total number of people who are not myopic. If we look down here, this is the proportion of each of these cells to the total. So this is the total. Expected values. The expected value for this cell right here of 82, which is the upper left-hand corner, we have 4 expected values. It's this marginal total times this marginal total divided by that grand total. That gives us the expected value. So we expect, by chance, given these marginal totals, we would expect to see 138 children in this cell. We only see 82. So our expectation is greater, and our actual observed was less than chance. If you were exposed outdoors, if you spent more than 35% of your time outside and had myopic. This is the idea of outdoor activity being protective, because this number is less than this number. We can look at the row percent. That's for those that were spent time outdoors, 10% of them were myopic. For those who were indoors, 19% were myopic. So again, you get this sense of protection. Over here we have a chi-square. Well, let's start with this one. This is the normal chi-square. We take well, this just calculates all of the things. This has kind of a special formula that takes a lot of shortcuts, but that gives us the uncorrected chi-square. We have a chi-square with continuity correction. That's where we subtract 0.5 from everybody in order to overcome this limitation of a 2 by 2. And then there's a chi-square correction with the same idea as the continuity correction by this guy named D'Agostino. Now, the continuity correction is very conservative, and D'Agostino's correction is not as conservative, but seems to simulate pretty well the one. So really, this is a better continuity correction than the one that's traditionally used, but generally speaking, you don't ever see it. Anytime your cell sizes or your total is greater than 60, you don't need to do continuity correction. But if it's less than 60, you should do some sort of continuity. The other assumption is chi-square is only appropriate if the expected values, these values down here, are all greater than 5. 5 or greater. If they are not, then really the chi-square is not appropriate, and you'd go to another test like Fisher's exact or something, and I don't have that in my spreadsheet. So let's look at some of the other measures that we look at. We have the odds ratio is calculated. It uses these proportions to do it. There is the standard error of the odds ratio. Notice that this is the square root of all these proportions and multiplies it and divides by the odds ratio itself, or divides the sum of all these different values to there. So that gives us the standard error, and then this odds ratio is used. Sometimes there's a cell size that has 0, and the whole thing blows up in that case. So we use a odds ratio that's modified, and basically what it's modified by is it adds 0.5 to each of the cells in order to get away from that problem of not being solvable with a 0 in it. Here we get the confidence interval for the odds ratio, 95% confidence interval. And sometimes we use log odds because odds go from 0 to 1 and 1 to infinity. When you take the log of that, it goes from negative infinity to 0 and 0 to positive infinity. So sometimes log odds are used. Relative risk. Relative risk is just the proportions here, the ratio of the proportions. So it is really the number that we're going for. Odds ratio is an approximation of relative risk, and we only use it when we cannot calculate relative risk directly. Here we give the confidence intervals for that, and we have here attributable risk. Attributable risk is the difference in the proportion. So we have 10% myopes in the exposed group, 19% in those that don't go outside. So the difference is the amount of risk that can be attributed to being outdoors, and that's 9%. And then we have this concept of number needed to treat is the reciprocal of the attributable risk, and that says that basically 11 kids. So if 11 kids are encouraged to go outside and spend more time, and actually do go outside and spend more than 35% of their time, free time, outdoors, you will get one kid that is saved from myopia. So that's the number needed to go outside in order to save one case of myopia. Now, there's a number that's over here. I think that shows up. Yeah. One of the problems is that odds ratios consistently overestimate the effect. For example, in our table, the relative risk is 52 and the odds ratio is 47. Now, by overestimating, we mean further away from 1. So these numbers are less than 1. So 47, an odds ratio of 0.47, is further away than the actual relative risk in this case, which is 52. You can compute relative risk directly if the subjects entered the study randomly. A lot of times people will do a case control study and they'll find, for example, 100 myopes and then compare them to 100 controls. You cannot compute relative risk directly in that situation. So you do the odds ratio. But there's a problem. If prevalence is high, then if prevalence is high defined as greater than 10%, then the odds ratio is really not a good estimate. Now, in this case, you have to enter prevalence on your own. Now, I've put in 40%, but I've computed over here. There is the computation using the control group. So if you are control, you're inside, and the total, that would say that people that aren't impacted, if just regular old kids, are 19%. This probably isn't the best example of a way of calculating prevalence in just the nature of this study. But it would be like if you did a a study where you randomly went out and you looked to see what is the prevalence of myopia in the population, and then plug that number into your prevalence. But let's use that for now. 0.19 is our prevalence of myopia. And we base it on this down here. So for this particular study, the prevalence was 0.19. Now, if we look, so we have down here actually a formula that allows you to estimate the relative risk from the odds ratio. So the odds ratio is 0.48, and then we have a little formula that we use to estimate the relative risk, and it uses the odds ratio and the prevalence to come up with an estimate, which is 53%, which you can see is the actual estimate that we got. So if we use the correct prevalence as defined in this case, the way we defined it here, then we can see that the relative risk is actually a little bit less than the odds ratio. If our prevalence was 0.4 or 0.75 if we were looking at Asians, being outdoors would be much less in terms of the risk, that the actual relative risk in this study. So it's important actually to report relative risk whenever you can, because it is a more honest representation of what the actual risk is. If you're reading a paper and they give you the odds ratio and they don't report the relative risk, then these are just numbers you can plug in yourself. You can plug in the odds ratio that you're given and your guess at the prevalence and get the actual risk. So that's the spreadsheet. Again, be very careful about how you put in these numbers. Exposure plus minus, disease plus minus, all of these numbers will be different if you don't put it in the exact right order. So order is very important. So these numbers plus prevalence will allow you to find all these different options.